3.3.1 Properties and Laws of Logarithms. So we have our basic properties that we've talked before. So we know we have our common logarithm, which is base 10, and also natural log, which is base e. Remember, they're only defined when you're taking the log or natural log of something that is greater than 0. Anytime we're taking the log or natural log of 1, it's always equal to 0. The log of this base of the same number is always equal to 1, so the natural log, and of course this is base e of e would be equal to 1. Here you want to fix this. This should say the log base 10 of 10 to the k power is equal to k. Over here, the natural log of e to the power of k equals k. And then over here, I forgot to write the equals the v, so 10 to the power of log base 10 of v is equal to v for every v greater than 0. And the same thing over here, e to the power of natural log of v would be equal to v. And we talked about those properties before, so that's why I'm just kind of going through them, but make sure, of course, you fix number 3 and number 4. So we can use these properties to help us solve equations, or logarithmic equations, or exponential equations. And again, remember, when the base is not written, it's base 10, so if it helps you to actually write in that 10, that's fine. If I'm solving the logarithmic equation, I always want to do the order of operations backwards. I don't have anything added or subtracted to the log, nor do I have anything in front being multiplied or divided, so I know that I can go ahead and put this in exponential form in order to help me solve, because the only way I can get the x minus 3 out of the log is to use exponential form. So this is 10 to the power of 1 is equal to x minus 3. So when we solve, we're just doing the 3 and adding it to the other side, so x is equal to 13. The reason I bring these problems up, though, is because we have to be careful, because remember, you cannot take the log of 0 or a negative number, so I have to make sure this is in my domain. So for my domain, I know that x minus 3 has to be bigger than 0, so that tells me that x has to be bigger than 3, so my domain would be then 3 to infinity. This is in the domain, so it works out. This problem says you solve, but we'll go ahead and do it together. So for this problem, again, the reason it's the same as the other one, except for we added that plus 3. So the reason I did that is to remind you that you are following your order of operations backwards when solving. So you want to subtract the 3 first. And now we have the log, and again, if you want to write base 10, you can, of x minus 3 is equal to negative 2. Now I can go ahead and solve this by putting in exponential form, because that's the only way to get this out of the log. So 10 to the power of negative 2 is equal to x minus 3. So 10 to the power 2 is 1 over 100, or you could write it as a decimal, 0.01 is equal to x minus 3. And now we can go ahead and add 3 to the other side to get 3.01 is equal to x. And now, again, we have to check the domain. Is this bigger? So the domain is the same as the domain from the last problem, which is x greater than 3. So this is bigger than 3, so therefore this works out as well. Next, we're looking at the product law of logarithms. So remember, this is for x values and y values that are greater than 0, because we can't take the log of a 0 or a negative number. So we learned last year that if we have the log and then we have the product of two numbers, we can separate that using addition. So the log of x times y is equal to the log of x plus the log of y. So this is the expanded form. Whereas this side is just written as a single log. So same thing for natural logs. The natural log of xy is equal to the natural log of x plus the natural log of y. So for this one, it says, for number 3, we want to use the product law of logarithms to evaluate each logarithm. So for this, we're given the log of 3 is equal to 0.4771, the log of 4 is equal to 0.6021, and we want to find the log of 12. So using my product law, because that's what it told me in the problem, we know that if we're given the log of 3 and the log of 4, and we want to find the log of 12 without our calculator, this is using the product rule, so 3 times 4 gives you 12. So really we're doing the log of 3 times 4, which is equal to the log of 12. And now we can go ahead and use our product rule, so that would be the log of 3 plus the log of 4, And they gave me those values, so really I'm doing 0.4771 and adding that to 0.6021, and then all I have to do is add those values together to get 1.0792. So of course the next problem is similar to this one, except for we're using the natural log. So the natural log of 3 is right here, and the natural log of 6 is here. We want to find the natural log of 18. So the natural log of 18 we know is equal to the natural log of 3 times 6. So we can use our product law and separate these, or I should say expand them. So the natural log of 3 plus the natural log of 6. And when we do that, we can now use these values and plug them in. So the natural log of 3 is 1.0986 plus the natural log of 6, 1.7918. And when we add those together, we get 2.8904. So if you don't remember from last year, you may be asking, well, why does this rule work? So if you recall that the answer to a log is an exponent. So if you think about exponential form, if I have x to the power of 3 times x to the power of 7, anytime I'm multiplying something with the same base, remember we add the exponent, so this is really x to the power of 3 plus 7, which is equal to x to the power of 10. So if you think about your logarithmic form, it makes sense that if you're taking the log and of the product of something, that is equal to the log of x plus the log of y, because the answer to a log is an exponent, so you're adding that the two exponents essentially. So let's go ahead and look at the next one. So the quotient law of logarithms, if you have the log of x over y, it's equal to the log of x minus the log of y. Same thing for the natural log. And again, if you think about dividing two numbers with the same base, if we think about this in exponential form, this is really x to the power of 7 minus 3, because when we're dividing something with the same base, we subtract the exponents. So this would be equal to x to the power of 4. And so that's kind of where this quotient law of logarithms comes from. So this says use the quotient law of logarithms to evaluate each logarithm. So right now we're going to evaluate the log of 40, or sorry, evaluate the log of 5, given the log of 40 equals this and the log of 8 equals this. We want to find the log of 5. So how do we get 5 from 40? Well, we divide the two numbers. So this would be the log of 5. We know is the same thing as the log of 40 divided by 8. And so if we are dividing these two, we can use our quotient property, which states that I can separate this using subtraction, or expand it, I should say. So the log of 40 minus the log of 8 is what we're looking at. And we know from what we were given, the log of 40 is 1.6021 minus 0.9031. And then all I have to do is combine these two. So when we do that, we get 0.6990. And then we have the power law of logarithms. So if I have the log of v to the power k, it is equal to k. We can also say the same thing when we're doing natural log. So if I have the natural log of v to the power of k, it's equal to k. And again, you can, here are some examples, but you can also think about exponential form. So if I have x to the power of, let's say, 10, all raised to the power of 2, well, remember that means if we have a power of power, we multiply the exponents together. So this would be x to the power of 10 times 2, which is equal to x to the power of 20. So if I have x to the power of 20, well, what do? We multiply the exponents. So think about when you are doing this power rule, the answer to a log is an exponent. So basically, if we're bringing this exponent down in front and saying we have this exponent k times the log of v, which is also an exponent, so you have your exponent times your exponent. So it's kind of the same thing, it's just, again, a different form. So for question 5, it says, use the power law of logarithms to evaluate each logarithm. So we are given that the log of 25 equals this, and we want to find the log of the fourth root of 25. So anytime I'm working with radicals, it's usually a lot more helpful to rewrite this as a radical. So remember that the log of the fourth root of 25 can be written as the log of 25 to the 1/4 power. Now we can use our power of law of logarithms by bringing this down in front. So that exponent is 1/4 times the log of 25. So that's like an exponent times an exponent. We're given that the log of 25 is actually equal to 1.3979, and then all we have to do is go ahead and multiply that. So when you multiply that, you get 0.3495. So for the b, you can, of course, do the same thing. So for this one, we have the natural log of 22, and we want to take the natural log of the square root of 22. So this is the same thing as the natural log of 22 to the 1/2 power. And again, that power is going to be moved in front by that property. So 1/2 times the natural log of 22, which is 1/2 times 3.0910. And then when we simplify, we get 1.5455. So those are our three properties of logarithms that we are going to use to help us with these next equations. So when you're writing a logarithmic equation as a single log, which means only one log in your equation, you want to put your final answer back in form of radical if possible. So that means if you have fraction exponents, you would want to put them in radical form. We don't want any numbers in front of the log or natural log, so we bring those up and make them exponents. And usually it's a lot easier if you just simplify from left to right. So for 6 and 7, it says write the following equations as a single logarithm. So you guys are going to do this problem. I'm going to go ahead and do problem number 6. So if I want to write this as a single log, that means I need to get rid of these 3 logs, or I should say combine them into one log. So the first thing I would notice is I have that 3 in front. So I'm actually going to bring that up as an exponent. So I have now the log base 10 of 8x plus the log base 10 of x to the power 3 minus the log base 10 of 2x squared. So we know that our first property was the product law of logarithms. So if we have 2 logs that are being added, we can actually multiply this is actually what's inside the log is called the argument. So we can multiply the arguments together and write it as one log. So this would be the log of 8x times x cubed minus the log of 2x squared. And of course we can simplify this. So this is the log of 8, and when we multiply something with the same base, you add the exponent. So log of 8x to the power of 4 minus the log of 2x squared. Now we can go ahead and use our quotient law of logarithms, which states that if I have 2 logs being subtracted, I can divide the arguments and, of course, write it as a single log. So this would be the log of 8x to the 4th. The one you're subtracting goes in the denominator, so the argument here is 2x squared, so over 2x squared. And now we have written this as a single logarithm, and the last step would actually be to simplify. So 8 divided by 2 we know is 4. So this is the log of 4, and then x to the 4th over x squared. Since we have something being divided with the same base, you subtract the exponent, so 4 minus 2. So that gives us x to the power of 2. So this would be my answer. So again, what did we do? We wrote the equation as a single logarithm using our properties as we went along. So why don't you go ahead and see if you can do number 7 on your own. And I'll give you a hint. It's probably a lot easier to rewrite your radicals as exponents first, so that might help you out. Looking at the next one, we're simplifying 8 and 9. So simplifying, again, means the same thing. When you're trying to simplify, you want to try to write it as a single log and get it down to one expression. So for this one here, the first thing I would notice is I have these radicals. So a lot of times I feel like it's a lot easier to write a radical as a fractional exponent. So this would be 2 times the log of m to the 1/4 power over m plus the log of 100 m cubed, and this is a square root, so that would be to the 1/2 power. Then I remember that if I have a number in front, I can bring that up as an exponent. So this would be the log of m to the 1/4 power over m squared plus the log of, and again here we have 100 m to the power 3 all to the 1/2 power. So before combining these two, I would probably simplify this because I know I have two things being divided with the same base, so I could subtract the exponents. I also have a power on the outside, which means I need to do the power rule. Same thing over here. I have an exponent on the outside, so I can do my power rule of exponents. So first I'm going to do the power rule. So remember that means that you multiply all your exponents by the number on the outside. So this would be the log of 1/4 times 2 is actually 1/2. So the log of m to the 1/2 power over, and remember this m is to the power of 1, so 1 times 2 is 2, so m squared plus, this is going to be the log of 100, and then this is to the power of 1, so that also needs to get the exponent, so 100 to the 1/2 power, and this would be m to the 3 times a half would be 3/2. And then we can go ahead and simplify. So remember that you subtract the exponents. So this is going to be the log of m to the 1/2 minus 2 is going to give me m to the power of negative 3/2. So again, 1/2 minus 2, you need a common denominator. So when you do that, this would be 2 over 2 to get your common denominator. So 1/2 minus 4/2 is where we get the negative 3/2, in case you're interested. So plus, and then over here, this is the log of, well, if I have 100 to the 1/2 power, that's the same thing as the square root of 100, which we know is equal to 10. So this is 10, and then times m to the 3/2 power. So now remember that we are trying to simplify this. So I can go ahead and rewrite this as 1 log, or I can bring these exponents down and try to simplify it that way. It's just kind of a preference thing. So I'm going to go ahead and just combine the logs, because simplify means we want to try to get one term if possible. So if I have 2 logs that are being added, I'm going to be using my product law of logarithms. So that means I'm going to be multiplying these terms together. So we have the log of m to the negative 3/2 times, that's 10, times the m to the positive 3/2. And remember that when you're multiplying something with the same base, you add the exponents, and notice I have negative 3/2 plus 3/2, so negative 3/2 plus 3/2 is 0, and anything to the 0 power is 1, so that's gone. So we get the log of 10 left. And now we're not finished, because we can actually evaluate this. So, because again, the question says to simplify. So if we can go ahead and finish by evaluating it, we're going to go ahead and do that. So we wrote it as a single log. And now we know this is log base 10 of 10, and we know that's actually a property. So we know, because if we rewrite this in exponential form, 10 to what power is equal to 10? Well, we know that that's going to be a value of 1. So log base 10 of 10 equals 1. So simplified, this problem is equal to 1. So why don't you guys go ahead and do this one on your own, question number 9. And let's go to the next problem. So now we went from the expanded form to writing as a single logarithmic equation and then also simplifying. So now we're going to talk about expanding. So when you're expanding logarithmic equations, for this you don't want any radicals, because remember, if you have a radical equation, you can rewrite that as an exponent, and then you can bring that number down in front when we're talking about the logarithmic problems. So no radicals in the equation, no exponents, so always bring those down using the power law and expand left to right. So for this problem here, the first thing I would notice is that radical, so I'm going to rewrite that using an exponent. So log base 3 of x times y to the 1/2 power over 2w. So usually I like to get rid of that division first. So since these are being divided, we know that we are going to be using the quotient law of logarithms. So we can use subtraction to separate those, or I should say expand them. So log base 3 of x times y to the 1/2 power minus the log base 3 of 2w. Then right here, these are being multiplied, and the 2 and the w is being multiplied. So now I can go ahead and use my product law of logarithms and expand these using addition. So this would be the log base 3 of x plus the log base 3 of y to the 1/2 power. Now for this next part, when you expand these, you have to be careful, because notice that both of them are in the denominator here being subtracted. So I'm going to actually put parentheses here because we're subtracting both of them. So this would be minus the log base 3 of 2, and these is being multiplied, so plus the log base 3 of w. And if we keep going, we know that we don't like to have powers in our expanded form, so that's going to become 1/2 times the log base 3 of y. So the log of 3 base 3 of x, sorry, plus 1/2 times the log base 3 of y. And then here we have that negative, so we're going to want to distribute that negative to both of these terms. So this is minus the log of base 3 of 2 minus the log base 3 of w. And this would be my final answer. So this is the expanded form for the log base 3 of x times the square root of y over 2w. And again, you have to be careful, because a lot of times students forget to distribute this negative to both terms, because again, both of them are in your denominator, so that's why they're both being subtracted. So why don't you guys go ahead and do number 11 on your own. So a lot of times these problems are just going to take some practice, which we'll do in class tomorrow.